All right, well, we might get started then. So it's my great pleasure to welcome Professor Elfatih Eltahir from MIT. Professor Eltahir's group works on a range of problems related to climate and hydroclimate, and his work has been deeply influential, I'd say, in transforming hydrology from a largely engineering discipline to a science in its own right. He got his PhD from MIT in 1993 and among many awards received AGU's Hydrologic Sciences Award in 2017. His group has been doing a range of interesting recent work, including work on moist heat stress, on the hydrological drivers of malaria transmission, and problems related to water resource management in Africa. And I believe we're going to hear a little about each of some of these topics today. So welcome, Fatih, and over to you.
Well, thank you very much, Kagan, and thank you. Good afternoon, everyone, and thank you for the invitation to share some of our work with this group. I would like to talk to you today about our research on regional impacts of global climate change. And the motivation for that, of course, has to do with the changes that's happening in the chemical composition of the atmosphere. This is the famous CO2 chart, which I think more of as the logo for climate change, and she updated until very recently, and it keeps going up. I tell the students that this is a very stubborn curve. It doesn't, you could look the other side and not address climate change, but it just keeps going up. We know what's causing that. It's caused by emissions of carbon dioxide due to human activity, burning of fossil fuels. This is the latest estimate of that, and it shows the impact of the COVID, small decline here, but sure, things would recover and keep going up again. But it's not only CO2 that's behind global climate change, it's methane and nitrous oxide and other greenhouse gases. And the result of that is the observed global warming, very well documented in observations. This is the picture for the 20th century. And the observations shown here in black and model simulations agree in basically simulating the observed trend of temperature as forced by changes in the chemical composition of the atmosphere. So this is all well known. Projecting into the future, there are different potential scenarios depending on what kind of mitigation effort is adopted, from RCP 8.5, close to business as usual, to very optimistic scenarios like RCP 2.6. Here with this slide taken from the Global Carbon Project, it has a hint of the debate about climate change, which tend to be really carried at the global scale, the Paris Agreement, the 2 degrees centigrade target, and that's actually part of what I will focus on, how appropriate is that focus on global scales. As you use those different scenarios, you could project temperatures into the future. And this is the radiative forcing as time goes, and the temperatures by the end of the century, depending on which scenario we are going to follow. However, the problem with all that is that when you see how society is reacting to those projections, you find the picture is quite disappointing. This is again from the Global Carbon Project. It shows how, every time we follow this process of projecting future climate, and then you, in hindsight, you go and look back, you find that the historical emissions growth over the period has been close or at the highest level, or the highest scenario, or the worst case scenario, which is basically, it indicates that society, global society, is not taking this problem seriously. There is no enough effort that would basically limit emissions and start reducing these rates of growth in the emissions of greenhouse gases. So why is that? Some of it has to do with how people perceive the problem. Most people think that climate change will harm Americans, but they don't think that it will happen to them. This is a conclusion from an article was in the New York Times a few years ago. It shows here in red is that the majority of people think that global warming will harm people in the US, but it's really a small minority that they think that it will harm them personally. You know, recently with the COVID-19 and how society reacted to it in a very robust way, trillions of dollars throwing on it, I wrote a short article, which I called it The Power of Here and Now. And I tried to compare COVID-19 versus climate change. COVID-19 is a problem that we have it here, impacting us now. And so you see how the reaction at the national and the global level have been very, very strong. Climate change, on the other hand, people perceive climate change as something that's going to happen over there and is going to happen then, sometime in the future. And while you know, the perception that is going to happen over there is something that we could work in trying to correct, is undeniable that climate change impacts mostly are going to happen sometime in the future. So that's something that could not be avoided. So a lot of the research in my group has been focused on how can we really better inform society at local, regional scales about how climate change is going to impact them directly, how climate change is going to impact processes that people care about. And so the story that I'm going to share with you today, and this is like, you could think of this as my conclusion slide, the story that I'm going to share with you has two sides to it. First, in order to accurately define risks from climate change and better inform society, we need to focus on regional and local scales, project impacts of climate change at those scales, focus on processes that people care about. The global focus that usually we have when we talk about the Paris Agreement and so on, that's not enough. The second side of this story, as we do that, as I'm going to show you through a set of examples, we discover that what I call all climate change impacts are local. You know, you hear about the phrase that all politics is local. You know, I am suggesting to you that all climate change impacts are local. And I mean by that, incorporating the local context in terms of natural context or economic, political, or social is critical for understanding how climate change may impact societies around the world. So the question of looking at local and regional impacts is not simply a question of downscaling, although that's something I engage in, downscaling global projections using higher resolutions, but also engagement with the processes that people care about and presenting the impacts of climate change in terms of how those changes are going to influence what's happening on the ground in those societies. So as I'm going to go quickly through 4 examples, hopefully if time allows, I plan to go through 4 examples. As I do that, I would hope that you focus instead of the details of each example on the thread that combines all of them. And the thread is basically summarized in these 2 points. So the examples I would like to share with you are drawn from research done by my research group at MIT, focusing on 4 different contexts. One of them is agriculture in the American Midwest. The second one is extreme heat waves in Asia, malaria in Africa, and water in the Nile. Very diverse and different kind of problems. So let's start with agriculture in the Midwest. As you all know, the Midwest of the US is one of the most productive agricultural regions. It has huge economic and socio-political role in this country. This is estimates of the hydrologic cycle from an old paper by one of my students for the different components of the hydrologic cycle over Illinois. Illinois has one of the best data sets as far as the complete hydrologic cycle, including not only the atmosphere, but also the soils and the rivers. And what I would like to draw your attention to here, if this is precipitation in the continuous line, and precipitation is very well documented and known in this area, we have a very good estimate of evaporation here. This is an estimate that we got based on analysis of the atmospheric water balance and the soil water balance over Illinois. It's shown here in a dashed line. And you see here during summer, you have basically evaporation in excess of precipitation. And so the hydrology of the American Midwest is very sensitive to what's going to happen to precipitation and evaporation in summer. And directly related to that is what's going to happen to agriculture in that region in summer, because a lot of this deficit in the hydrologic cycle is actually supplied by storage in the soil and storage in the groundwater. And depending on how this deficit changes in the future, that may result in conditions where the soil becomes limiting for growth of plants and agriculture. So the data that analyzed recently by some of my research associates in the group, this is analysis of observations on precipitation on the left and on temperature on the right for summer for the period the last 40 years or so compared to the first 40 years of the 20th century, 1910 to 2050. And you see that the data show that precipitation did increase significantly over this region, while actually the temperature did decrease significantly, significant cooling here. So this is at the time in which people are talking about global warming. You know, this region of the world, it has been experiencing significant cooling. So when you take this region and put it in a context of other regions in mid-latitudes, you discover that this is the changes in precipitation and temperature across mid-latitudes, the same 30 to 60 degrees north. You find that this region of interest here over the American Midwest is basically exhibiting a very different pattern, where the temperature had been declining and the precipitation increased, unlike most regions in mid-latitudes. What that points to is to a potential role for land use change. Land use change has the same fingerprint, intensification of agriculture. For example, this is here production of corn in the American Midwest. You see how the productivity or the yield of corn has basically increased by a factor of 4 during the 20th century. The area did not change as much, but the production increased significantly due to investment in agricultural technology that increased productivity, it increased photosynthesis, and you'd expect evaporation too. So the fingerprint of the change that has been observed fits better with the fingerprint of land use change, and that's actually what had been confirmed. This is what the CMF5 models that have been run without accounting for changes in vegetation over or land use over North America. This is the kind of increase in precipitation that they simulate on the left, and the kind of increase in precipitation that's simulated in my research group by accounting for those changes in vegetation and intensification of agriculture. What this points to is that what we observe when we come to look at climate change and we focus on the Midwest, is really land use changes seems to be a more significant process than global warming and the changes in the chemical composition of the atmosphere. This is here a PDF that shows the percent change in precipitation observed. In green, what you get from agricultural intensification, and in yellow, what you get from basically all natural and other anthropogenic forces like greenhouse gas emissions and so on. So that's the first case. It's really when you look down to a global climate change, you find more land use change and its impact, and less of the global warming fingerprints. Looking into the future, these are different models and how they simulate precipitation vary significantly across models. If you pick the wettest model and the driest model, those happens to be the German model and the NCAR one. They disagree basically on what kind of changes are going to happen in this region. The German model, the ECAM model, basically project increases in precipitation, and the NCAR model projects significant declines in precipitation. And these changes actually, if the ones predicted by the NCAR model, if they materialize, would have significant impact on agriculture in the Midwest. However, again, looking at the data from Illinois for the last 30 years, this is a very unique data set. If you look at precipitation anomalies, stream flow, root zone soil moisture, groundwater level, temperature, all these variables average over a regional scale of the state of Illinois. In this case, they basically show that there is no significant change in the climate system as described by these variables. So that was the first example. The second example I want to share with you deals with extreme heat waves in Asia. And this is a study in which we focus on Southwest Asia, the area around the Persian Gulf. That part of the world, it has very high seasonality in terms of temperature. In this case, the temperature in summer gets to be very warm, and also the humidity in the area surrounding the Gulf is relatively high because of the existence of the Gulf itself. So in looking at heat waves, we proposed and we use in our analysis the wet bulb temperature instead of looking at the regular dry bulb temperature. The wet bulb temperature, I think many of you know the definition, but in case you don't, the temperature that an air parcel would attain if cooled by evaporating water into it until it saturates. The wet bulb temperature is not only functional, it's function of both air temperature and humidity, and it's a better variable to describe heat waves and heat comfort level. The cooling of the human body takes place, through many processes like radiation, conduction, and convection, but the most significant is perspiration. And that's in order to balance metabolic heat generation, you need to get rid of heat at the rate of about 90 watts per meter square. And the skin temperature, which usually assumes the magnitude of the wet bulb temperature, the critical value for the skin temperature is about 35 degrees centigrade. That relates to the inner body of the temperature of the inner human body, which is about 37 degrees centigrade. So in order to get rid of heat, you need to have at least a temperature, maximum temperature about 35, so that heat could be transferred outside of the human body. Otherwise, survival and habitability could be at risk because of that. There are indications from station data that stations in the region of Southwest Asia, in places like Abu Dhabi and Riyadh and Dhahran and Jeddah, have been increasing. The wet bulb temperature maximum experience in any year has been increasing, and is hitting values not very far away from the 35 degrees threshold. So because of that, we focused the study on heat waves using a model developed in my group. We call it the MIT Regional Climate Model. It has all the details of what you have in a climate model, and developed through many years and many PhD theses that were done at MIT by my students. We take that model and we tailor it to a significant level to the regional context. In this case, for example, the albedo of deserts is a very important process in Southwest Asia. And albedo used usually in climate models is not as accurate as you would like it to be. This is the case, for example, in which we tailor the albedo prescribed in the model to match the albedo that you get from the NASA estimates of the surface radiation budget. So you see that the albedo of the region and the albedo from the observations are very close to each other. And that basically improvement of land surface processes results in better representation of those processes, and for example, better simulation of those processes. And here is the comparison of the wet bulb temperature in the observations and in the model with significant differences. So based on those tools and based on those calibrated models, we project into the future what would be the occurrence of annual maximum wet bulb temperature. Actually, this is 30-year maximum wet bulb temperature. We constrain the model in the lateral boundaries by a select group of GCMs from CMF5. And we could then project what would be the maximum web temperature simulated by the model under different scenarios, RCP 4.5, RCP 8.5, scenarios of emissions of greenhouse gases into the future. And you see that under the case of RCP 8.5, the model simulates significant values, significant large values of web temperature in the area surrounding the Persian Gulf. Actually, values touch and exceed the 35 degrees centigrade threshold. So when this research was first published, it received a lot of attention because it showed a case in which, climate change without mitigation could, in some regions of the world, it could touch on limits of habitability for human societies. And however, if you think about it, this is happening in countries like UAE and Qatar and Kuwait. These are countries where people have the capacity to basically adapt and provide air conditioning and so on. We also look at PDFs of how these variables basically are going to change. For example, if you think of Dubai, a very popular destination, how the web temperature distribution looks like in the current climate, and how it's going to shift under the RCP 4.5 and the RCP 8.5, with extreme values under the RCP 8.5 exceeding the 35 degrees threshold that we talked about. So as I said, you could argue that societies around the Persian Gulf, they have the capacity to adapt and provide the necessary air conditioning and so on. We came up with an example where outdoor conditions could be necessary. This is again the local context, what people care about in that part of the world and around the globe. People care about Hajj. There are 2 billion Muslims, and a few millions every year go to Mecca to perform Hajj. There is some of the rituals are outdoor. You spend it outdoor without air conditioning. And the timing of this ritual basically follows the lunar calendar, and for some years it basically happens during summer. So also based on climate model simulations, we could project how the web temperature basically during those times in which the Hajj is supposed to take place. You see how the maximum of the web temperature and what values it gets. And this coloring here from yellow to orange to red follows what's caution, extreme caution, danger, and extreme danger according to the National Weather Service criterion for defining those conditions. And you can see here climate change unmitigated could result in conditions for Hajj that would be in the extreme danger level. So also this research, when published a couple of years ago, it received a lot of attention in societies and people who care about Hajj and aspire to go to Hajj every once in life at least. This is a map, however, of the maximum value of the web temperature averaged over 6 hours ever recorded according to the observational record. And when you do that and you present in yellow values that between 28 and higher, yellow and red, this is the picture that emerges. So if you are interested in heat stress, and this is not really projections of models, this is just what has been experienced in the last 30 or 40 years, you'll find that these are basically the hotspots, the area around the Persian Gulf, an area in South Asia, in the Ganges Valley, the Indus and Ganges, and there is also an area in the North China Plain in Eastern China. So we had a series of 3 papers actually that addressed studies for these 3 regions and documented how climate change is going to impact heat waves in these 3 areas into the future. So I would like to share with you here the results that we had for for South Asia. This is the Indian subcontinent, and you see how this is under the current climate. The Indus and the Ganges, and those are areas of elevated well bulb temperature, mainly due to the fact that these are represent valleys that receive moist air during the monsoon season, and that basically what's responsible for the high well bulb temperature distribution. Under RCP 4.5 and RCP 8.5, again, what this is projected that these areas in Pakistan, northern India, and Bangladesh are going to experience extreme heat waves characterized by well bulb temperatures that approach and in some few locations exceed the 35 degrees threshold. What's important, however, about this region compared to Southwest Asia is that this same area, the Ganges, where we are projecting the impacts to be maximized, are areas where you have very high population density. We estimate about 1 billion people live in these areas. Most of them are poor farmers. So you have hundreds of millions of poor farmers that rely on agriculture for their living. And so you could see how this is a region where the hazard that basically projected from climate change overlaps with the high vulnerability of the local population. And so consideration of the local context of the socio-economic conditions in this area would be very important in determining the risk that climate change imposes to society in this part of the world. And there are also projections that places in Bangladesh, the risk is not only that if you maximize, the hazard to a vulnerable population, then migration could be potentially a significant response from those populations, resulting in impacts that goes beyond the national borders. So let me move to a third example, which is very different. And as I reminded you earlier, I would like you to keep that thread that basically combine all these examples that I describing to you, which is the need to focus locally and regionally and project things that people care about. And you need to also think of that in the context of the local conditions, because that's an important factor in determining where the risk is higher than other areas. Malaria is a big problem. It's actually a disease of the poor. The hotspot for malaria is Africa, but it really is prevalent across the tropics and in Asia and South America too. This is the latest report from the WHO. In 2018, about 400,000 people died from malaria, mostly in Africa, mostly children under the age of 5. So recently with COVID-19, there is more interest on this overlap of poverty and risk from disease. So I think here, studying malaria and understanding how climate change could impact malaria was motivated by similar ideas. How does malaria relate to climate change? It relates to climate in very interesting ways. These two curves, the blue one here down represents the lifespan of a mosquito. So as the temperature increases in degrees centigrade, the mosquitoes live shorter. They die, more quickly. They have a shorter life. What's shown in green here is the time that the parasite needs to develop within the guts of the mosquito. And so with cool temperatures, it takes the life cycle of the parasite. It takes a long time within the mosquito. For warmer temperatures, the life cycle develops faster. And so you need to have mosquitoes living long enough for the parasite to develop within their guts. And so if the temperature is too warm, the mosquitoes will die faster than that. If the temperatures are too cold, then the parasite will develop slower than the life time of a mosquito. So this provides a window in the middle, an optimal temperature range. And this is the temperature range where you usually observe malaria to take place. So that's the connection to temperature. The connection to water is obvious, because these water pools that result from rainfall events provide the breeding sites for mosquitoes. So this is data from Niger, where in red you have the seasonality of rainfall. And this is cases of malaria in hospitals. And so basically, it takes some time between the occurrence of rainfall, the development of the pools, the breeding of the mosquitoes, until people catch malaria and go to the hospital. So in order to study this was a long-term effort in my group. It took like 10, 12 years. We started by doing field work in Niger. Niger is this country in Africa here. We looked at an area next to the capital, and we instrumented a couple of villages, Benizimbo and Zindaru, to try and quantify the connections between disease transmission and the environment. Benizimbo is maybe one of the most instrumented villages ever. All these spots here are locations for meteorological stations, soil moisture profiles, temperature data loggers. CDC light traps is the standard way to capture mosquitoes so that you could bring them and figure out what type of mosquitoes and count them. So we have indoor and outdoor light traps. We also have locations where there are pools. We incorporate data on soil, vegetation, temperature, rainfall, humidity, wind, and so that provides the database that we collected in order to be able to use it for development of credible models that would simulate how occurrence of disease would connect to the environment. The level of sophistication in these models is very high. Actually, they are much more detailed than models that people use these days to project things like COVID-19 and so on. So this is an example, the model developed in my group called HydriMats. It has basically a series of 3 models simulating the hydrology, the entomology, and the malaria transmission. Early stages of development of these tools, I had collaborations at Harvard School of Public Health with the late Andy Spillman. And so we have a contribution of entomologists in development of these tools. So the hydrology model predicts where the water pools form. The entomology model predicts where what the numbers of mosquitoes, and the immunology model basically predicts the prevalence of the disease itself. And it's a detailed model with a lot of measurable parameters. So there is no fitting here. These are parameters that all people have documented in lab experiments and field experiments. So this is an example of, for Benizimbo, for example, projections or predictions of the model of where the water pools are going to form, and then pictures like at the same time documenting that what had been observed in the locations where the model basically predicted the occurrence of the water pools. Similarly, we test the model in its ability to simulate mosquitoes, the number of mosquitoes, and in 2 different years, wet and a dry year, and its inability to simulate the prevalence, basically the presence of the parasite in basically people's, samples from blood samples from people in the villages. Having developed this model, we were able to define the relationship between rainfall, temperature, and the prevalence. And can you see how under conditions in which the temperature is in that ideal zone and the rainfall is abundant, you get a lot of prevalence. When the temperature becomes warmer, you basically the prevalence drops significantly because that basically kills the warm temperature kills the mosquitoes. So projected into the future, the region of West Africa is predicted to warm up by different degrees depending on the time period. These are 2 different models. Actually, they happen to be the same models I talked about earlier for North America, the NCAR model and the Max Planck Institute model. The models project wetter conditions in this region of West Africa, drier conditions in this region. And so based on those projections, we could diagnose what kind of changes we'll have in malaria conditions in the different locations within these subregions. And in general, we find that in this region of West Africa, the likelihood for climate change is not likely to worsen the malaria conditions. So remember that this region of West Africa is the hottest spot for malaria, not only in Africa but also in the world. And so the finding from this decade-long study is that under the condition that exists in this region and the projections from model malaria conditions are not projected to get worse as a result of climate change. However, in a subsequent study, a doctoral student of mine looked at Ethiopia. And Ethiopia, if you look at this map, is a region where now conditions are not ripe for malaria transmission. For those who are not familiar with the region, Ethiopia is highland, elevated regions where temperature is relatively colder than West Africa, significantly colder than West Africa. So this student of mine, Noriko Endo, instrumented villages in Ethiopia too, and to monitor things like the atmosphere, soil moisture, trap mosquitoes, and so on, and develop models that allowed for simulating of these nice cares for different locations, showing the relationship between the annual temperature and the R0, which is the reproduction number, showing the potential for transmission. So there is an optimal temperature, and if things are colder, that's not good for malaria. If things are warmer, it's not good. And here you show the fraction of West Africa that's located in these temperatures. So the red is West Africa. And so in general, West Africa is located around 30 degrees. And that's basically explains why when the temperature gets warmer, things are not necessarily going to get bad for malaria. However, what's shown in blue here, this is the Ethiopian conditions shown in blue. And most of the land in Ethiopia is located to the left of the peak. So you could imagine that with the warming, that will basically push things towards more optimal conditions for malaria. So again, the local context is important. You are looking at the same phenomenon. You are looking at malaria. You are looking at the same region. You are looking at Africa. However, depending on looking at West Africa or East Africa, the sign of the projection of how climate change could impact malaria basically is different. Ethiopia, things are likely to get worse with climate change. West Africa, which is now in our current climate, is the hottest spot. Things are not likely to worsen, remain the same, or improve as a result of climate change. So here, this is an illustration of what could happen in the Ethiopian highlands. Different elevations, the population is located in different elevations. There is a fraction of the population in green. Those are basically people who are already experiencing conditions where malaria is prevalent. In red, areas where malaria is going to creep into them. Basically, these are bands of elevation where the temperature is ripe. If things get warmer, then malaria would be a usual occurrence, endemic disease. And then in blue are areas that are located high enough in elevation, even with global warming, the temperature will not be suitable for malaria. So you could see here how, by this careful set of projections, you could really target locations where attention has to be paid by those who are interested to basically design and apply adaptation, efforts for adaptation to climate change. So this study, as I said, on malaria in Africa has been a long-term study. We published a book just a few months ago that summarizes our studies in Niger and our studies in Ethiopian highlands, and it's available through through Amazon. So the last example I want to focus on is water in the Nile. The Nile is a very interesting system. Is a microcosm for Africa. It has too many people, in places like Ethiopia and Egypt. Each of them, the population in each of these two countries exceeded 100 million. Very soon, in the next couple of decades, the population of the Nile Valley would maybe be similar or exceed the population of the US. This increases in population shown here. This is what's happening in Ethiopia. This is what's happening in Egypt and Sudan to a less degree. And this is the water of the Nile is not projected to increase any significantly. And so you could see how these countries with increase in population, the water per capita is likely to decline significantly, resulting in a lot of water stress and basically fueling a lot of conflicts on resources. The Nile had a lot of data and observations historically for a long time. This is now data for two of the main tributaries, Atbara and the Blue Nile, and for the period from 1960 until recently. So if you look at analysis on the moving averages for this, you discover that the mean of the flow had been increasing slightly, significantly, statistically significantly, but with a small magnitudes. The standard deviation, which is shown here in brown, has also been increasing. So the mean of the flow and the standard deviation describing the interannual fluctuations in the flooding of the river have been increasing. In an old paper in 1996, we described a relationship between the Nile floods and El Nino. El Nino is one of the most, actually the Nile flood is one of the most, one of the geophysical phenomena that's most correlated to the El Nino phenomena. The El Nino explains about 25 to 30% of the interannual variability of the Nile floods. And that has a lot of implications. One of them is that the coefficient of variation coefficient of variation in the Nile floods, which is shown here in blue, seem to correlate very closely with the number of El Nino and La Nina events. So there are decades in which you have enhanced number of El Nino and La Nina events, you have more variability on the Nile, which makes a lot of sense. There have been recently some research in the oceanography community about increasing frequency of extreme El Nino events, increasing frequency of extreme La Nina events. And that's basically could have implications to how climate change could impact the Nile floods. This is analysis of CMF5 GCMs. In red here is the average of the models, and in black is the observations. This is the moving average of the runoff, the average runoff simulated by the models, and what had been observed. And on the right is the standard deviation from the observations in black, and from the models you see it in red. And what these results are showing is that the mean flow of the Nile is going to increase by about 15% or so. However, the standard deviation is going to increase by 50%. Think about it. So here in the case, we looked at the Nile, trying to understand how the availability of water is going to change in the future. And we discovered that, yes, there's going to be more water available, small addition to that, 10-15%. However, that water is going to come with enhanced interannual variability. So you'll have more occurrence of floods and droughts. You see here into the future how the coefficient of variation and the number of El Nino and La Nina events, they track each other too. So the engineering solution to situation where you have more water, but it comes with more interannual variability, the solution is through adding storage. That's the, humans for a long time invented, reservoir storages, dams. They build dams, they store water, and they basically keep water from the dry years, from the wet years to supply water in the dry years. However, if you do that in the Nile case, you see here, this is the capacity of water storage in the Nile. The capacity had been increasing with time. The relationship between how much the return period that you design for and how much is the storage. For the current situation, you have a storage that would basically carry you fails once every 60 years. If you look at the relationship that comes from the enhanced standard deviation in the future, you'll find that the current storage would only be enough like every 38, 37 years. You'll have failure more frequently. And in order for you to preserve the same return period than what you have now, you have to basically increase your storage by maybe 100 cubic kilometers or so. So what this really early results, this preliminary results indicate that in order to adapt to climate change on the Nile, you need to basically build dams, small scale dams or large scale dams. You need to add more storage so that you could capture the water from the flood years to the drought years. However, the local context for that is that the Nile countries are having now a conflict on a dam being built in the Nile. So what apparently would be the solution for how you adapt to climate change is a source of a conflict now. This is a picture. This is the former President Trump with like representatives from like Egypt and Ethiopia. They came because they have to negotiate, an agreement on the dispute, and the dispute is about a new dam that this GERD here, the GERD that's being built, and there is no agreement on how to operate it and so on. So here again, the climate change taken in the local context basically present a different set of challenges that you may not anticipate if you just look at the global picture of how precipitation and temperature would look like. This whole issue, this led me to write a book. This came up like a year ago, in which the issue of climate change on the Nile is being discussed in the context of these conflicts on water sharing, but also in the context of increasing population. The population in the Nile Basin is going to double by 2050. And so as climate change would happen in this region, this is happening in an environment where the population is increasing fast and the conflict on resources is a reality in everyday politics. So these are the 4 examples that I wanted to share with you. And I hope that by looking at them, you could, see this thread that goes across of them, across all the examples. The need to really, come up with these local and regional projections so that people understand better how climate change is going to impact their life, but also the complexity that arises when you do that because of the how the local context basically help or plays a role in shaping the risks that could come from climate change. Here is my list of acknowledgements, including my students and postdocs, collaborators, and funding sources. So thank you very much.
Thanks very much, Fatih. So if you would like to ask a question, please raise your hand. And so at this stage, any questions for Fatih? Perhaps I'll start off with one. In your work showing sort of regions susceptible to moist heat stress extremes, including sort of parts of North India, in your sort of view, are there particular sets of characteristics of a region that most cleanly identify these sort of moist heat stress hotspots? So for instance, it's obviously not enough to be, in the tropics or to have high temperatures. I guess I was a little surprised even that places like the rainforests of the Amazon or the sort of Congo didn't appear to be sort of hotspots in those maps. So are there sort of defining features in your view that sort of summarize this sort of risk?
That's a good question. One of the main features is elevation. The Persian Gulf area here is basically a valley, with between mountains on the Iranian side and also in the Saudi Arabian side. So having low elevation is a factor. Another factor is there is evidence that this area of the Indian Ocean here, which is to the southwest of India and to the southeast from the Persian Gulf, is an area where relative humidity is going to increase because of some set of not as well understood processes involving the Indian Ocean. So there are going to be increases in relative humidity, and so the monsoon air that basically advex from this region and the air that advex from this region in the Persian Gulf would have higher levels of humidity, more than what you would just project as due to the increase in temperature, because the relative humidity itself will increase. Another process that we actually documented a lot for India and for China, we have another significant study in China I didn't talk about because of time, is the irrigation. And interestingly enough, irrigation actually increases the wellbore temperature. This is something that you may relate to, Kagan, a little bit. When we do soil rainfall feedbacks, we think of how soil moisture impacts the energy in the boundary layer. The wellbore temperature is a measure of the energy in the boundary layer. So the wetter the soil or irrigated lands experience enhanced evaporation and decrease in sensible heat flux. But the total energy flux, which is the sum of the latent and sensible heat flux, increases as a result of irrigation or other result of moistening. And that enhancement of the total flux of heat and accompanied reduction in the depth of the boundary layer would concentrate more static energy into a smaller reservoir in the boundary layer, which results in enhancement of the more static energy per unit mass, which directly relates to the wellbore temperature. So when it comes to heat stress, when it comes, the conventional, people conventionally think of irrigated areas as cool areas, which is true. But when you combine the humidity impact, the impact of humidity wins. And so we propose this first, and there have been a follow-up papers that confirm that irrigation is a factor that enhances moist heat stress. And that's it's actually very consistent with also some work I did early in my career, looking at soil moisture rainfall feedbacks, in which I argued that enhanced soil moisture does enhance moist static energy in the boundary layer. It's the balance between the change in evaporation and the change in sensible heat flux, which relates to the change in net radiation, because net radiation is the sum of the two, and that increases when the land condition have a situation where evaporation increases. So these are three factors that we think are important in picking those regions. The fact that all these are valleys, lowland areas, the fluxes of moisture that comes from the oceans into them, and the third factor is local irrigation.
Right. Yeah. Thanks very much. So we've got a few questions. So we'll go to John, and then Loretta, and then Jerry. So John Holdren.
Thank you very much. Thanks for that very interesting presentation. I had a couple of questions. One relates to the importance of extremes as opposed to averages. Certainly, some of the evidence about climate change impacts on agriculture indicate that the biggest sensitivity may actually be to extremes that may be very short-lived, but which seriously affect the survival of the plants or their productivity. And the second question has to do with heat stress. You mentioned the capacity of countries around the Middle East to cope with extreme conditions, perhaps wet bulb temperatures above 35 degrees C with air conditioning. But one of the issues, and I know certainly this is already an issue in India, is that in the hottest months in the hottest parts of the country, it becomes very challenging just for people to work outside, to work in agriculture, in fisheries, in forestry, in construction. And in many respects, that, of course, that set of risks is less amenable to air conditioning. And there's also a fair amount of analysis just showing reduced productivity of outside work as the wet bulb temperature goes up. I wonder if you have looked at those dimensions of the heat stress problem.
Yeah, this is a very good, I think it's a very good point. And this is what we were trying to do in this figure here, where we point to that the same crescent that stands out as of maximized hazard from heat waves, this is the same crescent that where people live from the population data. And because as I said earlier, these are the valleys, and the valleys is where agriculture developed. So the valleys is where is next to the rivers, where you have the fertile soils and where agriculture developed and where the populations did grow. But these are also the same locations where as we know, lowland areas are warmer than high elevated areas. That's simply what it is that the lowlands and are warmer, and so those valleys where people lived and developed their civilizations and agricultural practices are the areas that are hit by heat waves in the future. But it's not only that you have a lot of people here. This data also on GDP, it shows even by Indian standards, this crescent is the crescent where people are in general poorer. And this crescent is of course, is where a lot of the agricultural activity is. So this is as much detail as we got into this. We are currently involved in an MIT proposal to really focus on Bangladesh and to try and look even more closer at conditions there, and in partnership with MIT Lincoln Lab, but also with partnership with local NGOs that has access to things on the ground, and they could use information and projections about near future climate change to help people on the ground. Your other point about extremes is also well taken, although in my view, and this is a topic for an ongoing research now in my group, if the first slide I showed, which is actually has a very good estimate of the hydrology of the Illinois area. You see here in summer, evaporation rates in this part of the world are very high, and this is consistent with a lot of agricultural productivity that's happening there. There is, they go together, photosynthesis and evaporation. Here, and that exceeds the magnitude of precipitation, which tells you that significant part of that agriculture is actually supplied by water that's stored in the soil. So while extreme conditions that may happen in a day or two may have impact, I still believe that what happens at the seasonal time scale in how these components of the hydrologic cycle are going to change will determine to a large degree the soil moisture conditions at the most critical time. And the most critical time for the soil moisture conditions is toward the end of the growing season. Basically time scales of about August and so on. That's the time in which, the soil is potentially at higher risk of being stressed because of lack of water.
Great, Loretta.
Yes, I'm curious to what extent you've considered aerosols in these trends of cooling or warming. So several groups have pointed to aerosols as contributing to the warming all over the US. A number of studies have looked at the effect of aerosols on regional climate in India and China. I'm curious if you have plans to consider those.
Actually, we did not look. We recognize what those ideas and suggestions, but we have not in my group looked at aerosols specifically to try and understand their role in these processes. And they could be potentially playing a role in some of the cooling of temperature that we see in the American Midwest, but also we also have done a study on China, North China Plain. And it's also a region that experienced cooling associated with expansion of irrigation, and potentially aerosols could be playing a role there too. But it's hard to sometimes separate those impacts due to changes in aerosols and impacts due to changes on the land surface processes. Some of my colleagues at MIT look at those processes. Some of my colleagues at the Parsons Lab, and I'm aware of the potential importance of those set of processes. But this is not an area where my group is active in. It's not an area where we are active in.
Thank you.
And Jerry.
I start with a point of clarification. It was my understanding that storage. Let's take the Aswan High Dam, for example. There's a lot of water that's diverted into the desert, right, already because of a lack of a capability to store that amount of water. Is that correct? So I'm wondering, when you talk about storage going forward 40 or 60 years, even at present day, the storage is incapable of dealing with all the water that comes down and reaches the Aswan High Dam, and it's diverted. What can't be held in Lake Nasser is diverted into the desert. Is that true?
Yes, for some time that was true. It depends on decadal scale variability of the inflow of water towards that system. And so during the 1990s, I think, and the first decade of the 21st century, that was true that there was plenty of water in Lake Nasser, and as a result, the government decided to divert some of the water into the desert and create what they used to call a new valley. A new valley, the Nile Valley on one side, and they want to craft a valley into the desert with that water. That wasn't really a very well thought idea, and now it's abandoned with a lot of economic losses. The water now of the Nile, we have a paper that's in review now, is going to come very soon, in which we did a very detailed accounting of water used in Egypt, and the water is fully utilized. The water of the Nile that gets to Egypt's borders is fully utilized, but lately they have, when they get these flooding years, that high flow years, the Egyptians, they capture all that and they store it, and they make use of it in following years. But there is conflict now because other countries in the Nile Basin, mainly Ethiopia, they would like to build dams, and they would like to store water within their boundaries, and so that's the root of the conflict that's ongoing now.
Thank you.
Great. So we're at 1:05. So please join me in thanking Fatih Eltahir.
Thank you very much for your attendance.